Yes, it's clear.
Do you see it?
Yes.
Okay, let's start. Hello, everyone, and welcome to this World Quantum Day. Firstly, I want to thank Dr. Ahmed Yunus for this opportunity. This is a wonderful opportunity to give me this talk in this day. Then I will talk. I'm truly excited to talk about the fascinating approach, quantum computing approach, linear optical quantum computing, and I will share some of my master thesis work. Let's start. Here we will start with exploring why photons are powerful candidates for quantum computing, and then we will compare linear optical quantum computing with leading platforms. Next, we will look at how we can encode information on photons and how to do quantum communication or quantum information processing. And we will explore the basic tools involved in this processing. Then I will also highlight a use case application and an enhanced quantum search algorithm, which is a part of my master thesis or master research before wrapping up with the conclusion and future directions. So why we choose light for quantum computing? First, photonic quantum computing uses photons, the fundamental particles of light, as a physical carriers of quantum information. This offers several potential advantages. First, photons weakly interact with each other and with the environment, which leads to low decoherence and preserving the quantum state coherence for long duration. Secondly, unlike some other quantum technologies, a photonic system can operate at room temperature with no need for cryogenic cooling. Third, excuse me. Thirdly, the speed of light allows for ultra fast operation, which and potentially very rapid operations. Furthermore, integrated photonic circuits with waveguides and beam splitters pave the way for scalable and modular quantum systems. Finally, photons' ability to transmit over long distance makes the optical quantum computing key to the future quantum and the classical hybrid internet. So photons is a strong candidate for quantum computing and quantum information processing. Here, to put things into perspective, let us briefly compare between the photonic system of photonic qubits and other different platforms. Here we can see that photonic, regardless or even superconducting qubits and trapped ions, has its own advantages like deterministic quantum operation, like universal quantum circuits, and high fidelity, and also very fast quantum computation as gates acting very fast. Also, the compatibility with the CMOS in the case of spin qubits. Also, the photonic system excel in some other areas like room temperature. It works or it function or it operates in room temperature and it also has low decoherence in flight, and it to integrate with quantum optics and or photonic quantum integrated circuits. The best case for quantum or photonic quantum qubits, we also use it in communication and sampling, and also using hybrid networks between classical and hybrid internet. Indeed, Indeed, 2-qubit gates in linear optical quantum computing are currently probabilistic. We currently work with probabilistic gates in linear optics. We mentioned that the superconducting acts in deterministic way, but here in photonic quantum system, the 2-qubit gates is probabilistic, but fascinating progress is being made in this approach. Companies like Xanadu and Psi Quantum are leading the charge, pushing the photonic quantum computing closer to real world applications. So there is different companies like Xanadu, Psi Quantum, Quandela, which is working on discrete quantum optical quantum computing, working on this approach. Next. Now we will discuss how do we encode quantum information on the photonic system on the single photons. In linear optical quantum computing, information is encoded in photons, typically using degrees of freedom. Degrees of freedom like polarization encoding, like path encoding, like time bin encoding. We will illustrate each one, each case individually. Horizontal, in the case of polarization encoding, horizontal case or horizontal polarization represents the state 0, and vertical polarization represents the state 1, as we can see here. In the case of path encoding, we can split the photon wave into multiple passes or many passes, which allow us to use the computational basis as a path or directions or spatial modes. As an example, we will see in the next slide the dual rail encoding as an example of path encoding. Then time bin encoding, where early and late arrival times of photons form the computational basis, and this allow us for multiple computational bases, not only two computational bases. Something worth to mention here that polarization encoding is intuitive and a clear way to encode the photon, as it has only two states, even or either horizontal or vertical. Horizontal for 0 can represent 0 state, and vertical can represent one logical state in the qubits. The second case, or as an example of the second case, path encoding, if the photon is present in the first rail or the first path, we can encode it as a logical 0 state. And in the other case, if the photon is present in the lower rail or lower path, it can present the logical 1 state. And we can transform between polarization and path encoding using polarizing beam splitter and half wave plate, as illustrated in this scheme. We can use a photon here encoded in a polarization states, horizontal and vertical polarization in a superposition, and input to polarizing beam splitter, which separate the photon based on its polarization, which is polarization, and this transform between the path encoding and polarization encoding. Here, linear optical quantum computing, the term linear optical in linear optical quantum computing refers to the passive linear optical components which we can use it to manipulate the photons. After we manage to encode qubit on the photon into the photon, we need to manipulate it. So we use linear optical components or elements like beam splitter, which can create superposition and interference between passes, phase shifters, which modify relative phase between passes by angle phi with this equation. Polarizers and wave plates, which manipulate polarization states of photons. Polarizing beam splitters, which we mentioned before, that separates photons based on their polarization and transforming between polarization and the path encoding. And of course, mirror and delay lines for spatial and temporal alignment. These components form the fundamental for implementing quantum gates using only linear optics. So here we can see how to optically simulate quantum logic gates using spatial and polarization degrees of freedom. Here we can find the Hadamard gate, which is a very famous gate in quantum computing on two logic states. Can be implemented in linear optics using beam splitter, 50-50 lossless beam splitter, and associated with two phase shifters with minus half pi. The second gate is CNOT gate with a target on the polarization state, which can we manage it with or manipulate it using polarization rotator here on the bus 1. The second case, or the second gate, the third gate, is also CNOT gate, but here the target on the location state, and the control is the polarization, which can be implemented using polarizing beam splitter which reflect the vertical polarization and transmit the horizontal polarization. Now, one of the major challenges in linear optical quantum computing is the weak interaction between individual photons. That photons interact very weakly with each other, making the implementation of two qubit gates like CNOT gates, which is necessary to universal quantum computing, challenging or difficult using linear optical components. A breakthrough protocol in 2001 was done by Neil Laflamme and Melbourne, who demonstrate that scalable quantum computing is indeed possible using linear optics components. These components, or this protocol, which puts the basis for the scalable quantum computing, uses linear optical components like beam splitters and phase shifters, single photon sources, and high sensitive photon detectors, feed forward correction based on measurements, and importantly, both selection and ancilla photons, which are used to simulate photon interaction in a probabilistic way. Essentially, the non-deterministic two quantum gates, we mentioned before that all one qubit gates are made or done deterministic, using a deterministic case. But in the case of 2-qubit gates or entangled gates, it is non-deterministic, but we can do it probabilistically. We can realize it probabilistically, and we can know when it succeed. And it succeed only with specific measurements outcomes, and we can detect it with some measurements or some post selection measurements using photon detectors. Here, this is Nell's CNOT gate scheme, which uses or employs two ancilla photons. Here we can see it, two ancilla photons. This is a qubit. This dual rail qubit. This is the first qubit, and this is the second qubit. And we want to implement the CNOT gate. Here, the one qubit gate, Hadamard gate, is implemented deterministically using a beam splitter before and after a heralded controlled Z gate, controlled phase gate. So using two ancilla and two heralded detection after the operation, we can implement the CNOT gate in a probabilistic way using heralded detection. Here we can see the basic gate implementation in special optical modes. As we mentioned before, that all the qubit gates, one qubit gates, can be done deterministically using beam splitters or wave or phase shifters. That Pauli X gate can be done with only some mirrors in the paths or waveguides. Pauli U we can be implemented using two phase shifters and beam splitters between the two rails. Phase Pauli Z can be implemented using only one element phase shifter in the state one or the second rail. Hadamard gate, as we mentioned before, that we can use it use beam splitters associated with two phase shifters in the second rail. Here is this illustration for the interference or the action of 50-50 beam splitter, and this is the unitary matrix associated with it. This is the first rail, second rail, dual encoding qubit. The photon presented in the first rail. So after the beam splitter, it will be in a superposition between the two rails, which represent a qubit. On the bottom right here, we can see the Ralph's post-selected CNOT gate, which employs two vacuum ancilla modes, which is another example of probabilistic gates. I won't go deep in this case, but is important gate. Okay. To illustrate the potential of linear optical quantum computing, let's look at an application, our real-world use case application, and enhanced quantum search algorithm implemented using only linear optics components. First, I want to give some notes or some introduction for the quantum search algorithms. Quantum search algorithm started with in 1996. Grover proposed an algorithm which offers significant quadratic speed up compared to the classical search, reducing the complexity from O of n to O of square root n, which gives a quadratic speed up using a partial diffusion operator, or using a standard diffusion operator represented by this equation. On the right here, we can see the quantum circuit illustration of the Grover algorithm, which operates in order of square root n. This application has a wide. This algorithm has a wide application in areas like database search, graph problems, and optimization tasks, like the traveling salesman problem. Later in 2007, Yunus et al. Introduced an enhanced quantum search algorithm. دكتور أحمد يونس مجموعة من البروفيسورز introduced an enhanced quantum search algorithm using entanglement and partial diffusion operators. This is the equation for partial diffusion operators, which we can implement in the illustrated quantum circuit on the right here. Quantum the enhanced quantum search algorithm differs from the Grover algorithm that it uses one additional workspace qubit, which can do more or work in good manner in some cases that Grover fails. Here, the exciting thing here is that this enhanced quantum version can be implemented using using linear optics, making it a practical use case. In this enhanced quantum search algorithm, we will deal with an unstructured list L of size n, which we can represent it n equal to 2 to the power n lowercase n, which is lowercase n can be the number of search qubit we can use in the algorithm or the implementation. And we can also use an oracle functions that marks solution as 0 for non-solutions and 1 for solutions. By entanglement, we and store the results in additional qubits, additional workspace qubit here. In this case, we will consider the target solution to be in the state 1, 1. This is, for example. And here we can see the illustration, a quantum circuit illustration for this protocol. And now here is the most interesting part, the optical realization of the proposed algorithm by Yunus et al. Here, qubits are encoded in two ways. The search space qubits is encoded in the path degree of freedom, and the additional workspace qubit will encode it in the polarization degree of freedom, which will give me some advantages in advance. Here we can see the illustration or the optical setup, starting with a beam splitter, a beam of laser, starting with a beam of laser in horizontal polarization here, with initial state can be written as 0, 0, with the first qubit in the state 0 and the second qubit in the path realization qubit 0 in state 0, and also the third qubit can be realized by horizontal polarization. Manipulating the photons or the laser beam in this quantum circuit and evolving it, we can see the output state in this way. And this is the output state at this stage. In this stage, before the detectors, before the photon detectors, we can see the output state in this way. Here, which is worth mentioning here, is that encoding the workspace qubit in the polarization degree of freedoms decouple. Here we can see it allows us to decouple it from the detection process or detection measurement or final measurement using photon detectors. We don't need to measure polarization directly. We can ignore it. As we can see here, the target state 1,1 and entangled with horizontal polarization, and also the same state entangled with vertical polarization. So we can ignore the polarization state and detect the probability amplitude of the two terms in the same time using photon detectors. This simplifies the detection process and also improve the efficiency of detection and increase the probability of success. Here is the results of this setup. Results are impressive. We can see that after one iteration, the photon detector, the second photon detector, can detect the photon with probability. We can, as we can calculate it, about 81.25% after the first iteration. After the second iteration, we can see that the same detector can detect the photon with higher probability, which is about 95.31%, which give a high probability and high fidelity of the algorithm. But beyond that, over iteration reduces the success of probability success or success probability due to quantum interference. We can see after the third iteration, the probability or success probability reduces to about 42%. At the last, we can conclusion and put this in summary. And linear optics can offer a promising path towards classic scalable quantum technologies due to low coherence, and we can work at room temperature. Also, the KLM protocol established the foundation for scalable linear optical quantum computing. With even with probabilistic gates, and we need to put a line underline here. Probabilistic gates is very important in linear optics quantum computing. As we mentioned, the application the enhanced quantum search algorithm is used using linear optics as a use case for potential using of linear optical quantum computing. And it has some advantages in or important tasks in computational tasks. At the last, I want to mention that our future work focus on scaling the implementation to large databases, and we will explore also optical quantum computing using or with continuous variable, which is the most dominant in optical quantum computing used by Xanadu company. This is the reference we used for this in our research. And towards mentioned also to that our paper has been accepted and will be published soon. At the end, I want to thank you for your attention, and I'm happy to answer any questions you may have. Thank you, Dr. Ahmed.
Thank you, Ahmed, for this very interesting work. I know this work, of course, because I'm a co-author on this paper, and Ahmed did a lot of work, very excellent work in this paper, and I believe it will be published in a prestigious journal. So we can open questions. If anyone has any question, please raise your hand, or Muhammad Shahata. please, you can open your mic and ask directly.
مساء الخير والف شكر احمد والف
نور.
شكر دكتور احمد كمان. هو السؤال بس انت قلت في الثيرد iteration كان البروبابيلتي 42% وفي السكند 98 تقريبا وفي الفيرست كان ايوه دي فيرست اتش 1. يا ترى في تفسير ان في تفسير ان الثيرد iteration طلعت 42 انخفضت بشده، يعني في تفسير
هو
كده؟
ده بسبب الانترفيرنس وده بسبب الدي امبليفيكيشن افكتس الناتجه من زياده الاوفر iteration. ودكتور احمد يونس ممكن يقول لنا
This is normal. Yes, this is normal feature in any amplitude amplification technique. If we increase the number of iteration, the probability will go down again, and then it will go up and go down because it behaves like a wave. Actually, Ahmed should stop after the second iteration. This is the highest probability he can get. This feature in all amplitude amplification, even in Grover's algorithm, has the same effect. They call it in the paper overcooking. So if we keep iterating, the probability will go down again.
شكرا.
Yusuf, you can open your mic, please.
I had a question right now. It was said that one of the problems with CNOT gate and Hadamard gate was the weak correlation in between phonons. Is that correct?
I can't hear you.
Sorry.
Yes,
I can't hear you.
Your internet connection is not stable.
Can you repeat
there is
your
weak
question
correlation
again?
in between photons have weakly can interact with each other weakly in order to make a Hadamard CNOT.
If I understand the question correctly, he says.
مش ده السؤال. انا بقول الفوتونز مش بتكابل مع بعضها، صح؟ الكابلنج اللي بيتم ما بين الفوتونز بتعتبر ضعيف.
weak decoupling فالهاردوار جيت والسي نوت is not perfect on the optical quantum computer. This is your question.
I wanted to follow up on that by asking if, since photons cannot interact with each other strongly, why not use the interaction between photons and electrons or other charge carriers, which are much more significant, like interaction photons and electrons to make plasmons or what else to make the gates.
Okay, this is not our approach in linear optical quantum computing. This is another approach, but also used like trapped ions. We also use laser beam to control atoms and ions in a cavity. So it's also resist or our approach to use only only linear optical quantum computing and linear optics components like beam splitters, phase shifters, and this can't we can't do this using these components.
Okay, thank you.
So it's a different approach.
Okay, good.
Thanks. Do you get it?
Yusuf, we still have a question from Karim. Can you unmute, please? We cannot hear you. Can you check your mic?
Can you hear me now?
Yes.
Yeah, we can hear you.
How are you, Dr. Ahmed? Is everything okay?
How are you, Karim?
I'm good, and you? Your voice is breaking, or maybe it's my connection.
Okay. We hear you.
We can hear you. You can ask your question.
Okay, so I have like multiple questions actually. The first one would be what or which Python package did you use?
Which for this?
Python package.
Actually, we have done this theoretically, and we can calculate it using using our hands, and we can involve this or this setup.
Mhm.
We can use this elements to
Simulator is optical simulator, yeah.
no, I will answer this question, but this is not a simulator. This is an illustration using drawing illustration for what we have in theoretical, we can done in theoretical, but this is a photo from a Percival from Condella simulator, which can work on discrete variable quantum optical quantum computation. This is a Percival from Condella. Condella is a French company. Also, we can use some other platforms or Python packages like Xanadu, or we can Benylin from Xanadu for a continuous variable quantum
Strawberry
computation.
fields, right?
What?
Strawberry fields. Benylin is for
Strawberry fields and Benylin for quantum machine learning. Strawberry fields from Xanadu to continuous variables, and Benylin for quantum machine learning, also on quantum on photonic quantum chips.
Okay. Maybe you can also try something called photon weave.
What?
Photon weave. It's like a really new package.